All right, take two on inequalities. See if it works this time. An inequality is something that has one of these inequality signs rather than an equal sign, but you graph it the same way. So we are trying to solve a system of inequalities, which means there's two things to take into account, not just one. One of those things is that y has to be greater than or equal to 4x minus 1. The way you graph it is the same way you'd graph a line. You start with the -1 because that is the y-intercept, meaning it's the value of y when x is 0. If I plug in a 0 right here, then it's just 0 minus 1 or -1. It goes right here on the y-axis. Then from there, the other number, the 4, is a part of the slope. So we go up 1, 2, 3, 4. And if you remember the term rise over run, 4 is the rise. So what is the run? The run is 1 because there's no number beneath the 4. So any number could be written as a fraction. 4 could be written as 4 over 1. So that's the slope of that line. And then the way we connect those lines. So you remember, if you connect the lines, you draw this nice line. It's not a straight line, but the line is the solution if it's an equality. If it said y equals 4x minus 1. Those are all the places where the y value is 4x's minus 1. But that's only a portion of a tiny part of the solution here. We want all the times the y values are greater than 4x minus 1. So if x is 0, then y is -1, but actually anything above that works. All the way up, to infinity, all the way up here would work because all those y values are bigger than -1. So 5 works, 5,000 works. Okay, so anything above this line when it says greater than is a part of the solution. And below the line is a solution if it says less than or equal to. So I'm going to try to get a different color if I can get this thing to load. I have been having some computer struggles lately. Computer sounds like it's about to blast off. Okay. The next one, y is greater than x plus 2. So again, we're going to go to the y-intercept first. That's the +2 part. And where do we go from there? You're like, well, there's no number in front of the x. Okay, that means there's only one of them. There's one x. If there were more, they would tell us. So the rise for us is going to be 1. And what's the run? The run is also 1. Okay, so up 1 over 1 gets us to that same blue point. And so that blue point would be a really good point to investigate because this one needs to be a dashed line. When you draw a dashed line, you're saying that the line itself isn't the solution or isn't a part of the solution. It's only the barrier between solution and not a solution. So this one also says greater than, which means the solutions are above that line in the green shaded area. And it's red. Come on. And where all those things overlap, where those solutions overlap, those are the solutions to the system. So if it's in blue, shaded in blue, it's a solution to the first inequality. Shaded in green, it's a solution to the second inequality. Shaded in red, it's a solution to both. And let's go ahead and look at the point 1, 3, which is this point right here that I just drew in red, the point 1, 3. So is that a solution to our system? That's an x value and a y value. So if you look in the equations or the inequalities, you have x and y values. If you plug in 3 for the x value or 3 for the y value and 1 for the x value, you get this inequality, which says 3 is greater than 4 minus 1. What's 4 minus 1? It's 3. 3 is greater than or equal to 3 because it's equal to 3. So the point 1, 3 is a solution to that first inequality. But if we check the second inequality, we again are going to plug in 3 for y is greater than 1 for x plus 2. So you end up with 3 is greater than 3. But 3 is not greater than 3. 3 is the same as 3. So that is not true, which means that 1, 3 isn't a solution to this inequality or to the system of inequalities because it's not a solution to the last inequality. It's only a solution to the first. Next up, let's look at number 38, which is just kind of a silly situation that I made up to look at inequalities, a system of inequalities in a real world kind of context. So we have a Jake who is an insurance agent, and he has to go over insurance policies because he works at State Farm, obviously. And he has to go over a certain number each month. And so he's kind of looking out, he's already started his month and he's looking out in the future and saying, how many more do I have to work? Or how many more policies do I have to go over? Well, he started at, or he wants to get to 120. So 120 is his goal. And I'm going to draw a line right here at 120. And I'm going to draw a solid line because the number of policies he writes needs to be greater than or equal to 120. So 120 is like a solution, but it's not the only solution. He could write 140 or go over 140 policies. He could go to 175 policies, whatever. The more the merrier. So everything above that line is a solution to the first part of the inequality. Go away. All right, so let's finish this one. I don't remember where I left off, but we have to get to at least 120 policies. So anything above that line is good. Well, how are we going to get there? The number of policies that Jake has already gone over is 30 currently, but he adds to that 12 policies every single day, or that's the most he can add to it every single day. So after he does that every day, so that's why there's an X here. The X represents the number of days that he has been working on policies. And if he does 12 every day for 5 days, that's 60 more policies. Okay, but 12 is like the maximum that he could do. So the number of policies that he has could either equal this or it could be less than this. So that's what we're going to graph. We're going to start at 30. The slope of this line is up 12 policies per day. So 42, 54, 66, 78, 90. Draw that line, and then beneath that, those are all the solutions for the policies that he's written. So I mean, he may or has worked on. He may not really work on any policies over the next few days, so he may stay down here. But all of these are in the realm of possibility that he could work on this number of policies over this given time. So as long as it's up here above the 120 line, that would work. If after 16 days, he had made it to 135 policies, that fits, that goes within he had a month to work and he was able to get above the 120 threshold. So anything in the place where they were both shaded is a solution to that inequality. Next. We're going to stick with some inequalities here. I'm going to do number 41, but I'm only going to do the middle point here, and I'm not going to graph them. So we already graphed We already graphed a couple of these. This is no different. And if they overlap the shaded regions, then it's going to be a solution to the system. But sometimes it's just as easy or even easier to look at a point like 2, 0, which is an X value and a Y value, and see if that X and Y value creates a true statement in the inequalities. So for example, I could, using this inequality, plug in a 0 for the Y. Greater than or equal to negative, the X value is 2 minus 2. We get 0 is greater than or equal to negative 4. So is that true? It is true, which means that it's a solution to the first inequality. But if we want to know if it's a solution to the whole system, we have to work through the next part as well. So we can go to the next inequality and plug in the same point. So y is equal to 0, greater than or equal to 1/3 of 2 plus 2. 0 greater than or equal to, that would be 2 2/3. And that is not true. 0 is not greater than or equal to 2 2/3. So is it a solution to the system? No, because it doesn't solve both inequalities. But is it a solution to one of them? Yes. Which one? The first one. And that's what you do for each of those. You could graph them and then look at the graph, or you could just plug in those points the way I did for each of them. I'm going to end this one and start a new video where we solve systems of equations.